So at this point, we've been doing a lot with linear systems, and it's not really clear what this has to do with differential equations. And we're going to take the first steps now to get back to the idea of solutions to differential equations. Before we do that, though, we need to go back and reinforce some ideas that we've just discussed, because they're going to come back and haunt us very soon. First thing is this idea of the determinant. So if I have a matrix A, then one question is it invertible? Which is another way of asking, does the inverse exist? So we have a number of tools. One way is we just go to try to find the inverse and then see if things break down in the calculations. The other thing is we have this thing called the determinant. And there's different notations. One notation is that. The other notation is these straight bars. But the idea is, if the determinant is not 0, then the inverse exists. And why that's important is that if we want to find solutions to linear systems, then we would like to know whether or not a unique solution exists. And it turns out that if A inverse exists, there is a unique solution. And it also goes the other way. If there's a unique solution, then the inverse exists. So it turns out to be one of these things that if you show one, everything is going to be true. And if the determinant of A is 0, A inverse does not exist. And two things could be true. Either there are infinite solutions, or there are no solutions. And this is all going back to and referring to this system of equations AX equals B. And the way this is going to pop up is that we are going to try to ensure certain properties of linear systems we're going to construct. And so before we do that, we're going to just go through some examples and show how we use this when it comes down to parameters. So for example, suppose I have the following systems of equations: 3x plus 4z minus lambda x is 0. I also have 2x plus 4y plus z is 0. And I have x minus 3z is 0. And so what I would like to be able to do is I want to determine the values of lambda where there are infinite solutions. Now, just to be pedantic, notice when we work with AX equals B, in general, we have three options. There's a unique solution, there are infinite solutions, and there are no solutions. In this example here, because I've got all zeros, if I let x equals 0, y equals 0, z equals 0, then that's satisfied, and that's satisfied. So I can get rid of that option, and I now only have two possibilities. Either there's unique solutions or there's infinite solutions. And so the questions now is, how do I ensure that this is the case? Okay, so let's go back to our system, rewrite it, and we're going to recast it. So we started off with this question. I want to determine values of lambda so that following system has infinite solutions. And that solution was 3x plus 4z minus lambda x is 0, 2x plus 4y plus z is 0, and x minus 3z is 0. And I know that there is at least one solution, so that solution is either going to be unique or there's going to be infinite solutions. Now, let's put this into a linear system of equations. And here my unknowns, or my state, is x, y, and z. And on the right-hand side, I have all zeros. I'm going to be a little careful. I've got an x here and an x here. Another way to write that equation is 3 minus lambda all times x plus 4z equals 0. And notice my coefficient on y is 0. So that means for the first equation, my coefficient on x is 3 minus y, coefficient on y is 0, the coefficient on z is 4. So 3 minus y x plus 0 times y plus 4 times z is 0. Now going to the second equation, I have 2x plus 4y plus 1z. 2x plus 4y plus 1z is 0. In the last equation, notice there's a 0 on the y. So I'm going to have x plus 0y minus 3z is 0. So this is my matrix A. This is x. And this is B. So this is now in the form ax equals b. I know x equals 0 will work. And I want to make sure that there are other solutions. And that's only going to be true if the determinant of A is exactly equal to 0. Right? Because if the determinant of A is not 0, that means I have unique solutions. So the idea is I want to get a value of lambda so that the determinant is 0. And my matrix is 3 minus lambda, 0, 4, 2, 4, 1, 1, 0, minus 3. And I got to pick a row or column to do my determinant. And I claim that that middle column is going to be my best bet because of all the zeros. So let's see, so this is going to be plus, minus, plus. So this is minus, plus, minus. So I'm going to have minus 0. Now for this 0, if I remove the top row and the middle column, I'm going to have 2, 1, 1 minus 3. I'm going to have plus 4. If I remove the middle column and the middle row, this becomes 3 minus lambda, 4, middle row, 1 minus 3. And then for that term, so minus, plus, minus 0, and I get rid of the bottom row in the middle column, get 3 minus lambda, 2, 4, 1. Again, so I immediately see those are zeros, so I don't care about those. So I want this whole thing to be 0. And I can now, because this is a 2 by 2, I can immediately just take this determinant. So this is 4 times the quantity, minus 3 times 3 minus lambda, minus 4 times 1 is 0. And let's see, I can divide both sides by 4, and if I multiply the minus 3 through, I get minus 9 plus 3 lambda minus 4 is 0. If I add 9 plus 4, I get 13. So lambda is 13 thirds. Okay, so if lambda equals 13 thirds, there's going to be infinite solutions. And no inverse to this matrix exists. Right, so here, if lambda equals 13 over 3, there's no inverse. Let's do another example. I can ask, is the solution to w minus x equals 0, w minus 2x plus y equals 0, x minus 2y plus z equals 1, y minus z equals 0, is it unique? Okay, so let's see, what is my state? I have w, x, y, and z. So my state vector is w, x, y, and z. So I have 4 unknowns and I have 4 equations. So because it's 4 by 4, I can just do a determinant without going through and doing all the stuff. So I'm going to rewrite this system. Is a matrix vector. So w minus x equals 0. It's going to be 1w minus 1x, 0y plus 0z. Second equation is 1w minus 2x plus 1y plus 0z is 0. Third equation is 0w, 1x minus 2y plus z is 1. And the last equation is 0w's, 0x's, 1y minus z is 0. All right. The solution is going to be unique if the determinant of this matrix is not equal to 0. So I'm basically just going to go do exactly like what I did before and go from there. So what is the best thing to do? I could use the first column or the first row. I'm just going to use the first row, and I like that because as I go across, there's 2 O's or 2 zeros, and it's going to be plus, minus, plus, minus. So this determinant, I'm going to have plus 1. So now if I remove the first column and the first row, I'm left with minus 2, 1, 0, 1, minus 2, 1, and 0, 1, minus 1. I'm going to have a minus, minus 1. And then here I'm going to remove the first row and the second column. I'm going to have 1, 0, 0, 1, 2, 1, 0, 1, minus 1. And then here I'm going to have plus 0. If I remove the first row and the third column, I'm going to have 1, 0, 0, minus 2, 1, 0, 0, 1, minus 1. And finally, the last column. So I get rid of the minus 0 times. Get rid of the first row and the last column. I've got 1, minus 2, 1, 0, 1, minus 2, 0, 0, 1. And this is whatever, 0 times whatever, I don't care. And the question now is, what is this equal to? And again, if I get 0, the solution's not unique, if it exists. So let's rewrite that. So I had my linear equation, and it boiled down to taking the determinant of a matrix, and we've now decided it looks like this expression. Oops, this is a 1, 0, 1, minus 1, minus a minus 1. So 1, 1, 0, 0, 2, 1, 0, 1, minus 1. Is that correct? I believe that is consistent, I hope. Let's see. I think we're okay. All right, so now for each of these, I have to decide how to expand. Here I could either use the first row or the first column. I'm going to go with the first column simply because I used the row before and just want to do an example of this. Having said that, looking at this one, though, the clear winner here is the first column because of the zeros. so now here it's going to be plus, minus, plus. It's going to be the same thing here. So this determinant is going to be 1. So this is going to be minus 2 times the determinant. If I remove the first row, first column, get minus 2, 1, 1, minus 1. Yep. Oops. Minus 1 times. Now you remove the first column, first row, 0, 1, minus 1. And then plus 0. I remove the first column, last row, 0, minus 2, 1. And this is going to be minus a minus 1 is plus 1. So I'm going to have 1 times, I remove the first row, first column, 2, 1, 1, minus 1, minus 0, remove the first column, second row, get 1, 0, 1, minus 1, plus 0. I move the first column, last row, I have 1, 0, 2, 1. That's 0, that's 0, that's 0, so I don't worry about it. And notice these are now 2 by 2, so I can just plug straight into my formula. So this is going to be minus 2 times the quantity, minus 2 times minus 1, minus 1 times 1. This is going to be minus 1 times the quantity, 1 times minus 1, minus 1 times 0. Don't worry about that. And then close. Plus 1 times the quantity. It's going to be 1 times, so 2 times minus 1, minus 1 times 1. Close. And now I just grind it out. So don't have to worry about the 1s anymore. So this becomes minus 2. This becomes 2 minus 1. Minus 1 times, this is minus 1, minus 0. Then this becomes plus. So 1 times minus 2 minus 1. Is that correct? I think that's okay. So this becomes minus 2 times 1 plus 1 minus 3. So I get minus 2 plus 1 is minus 1, minus 3 is minus 4. So the solution exists and it's unique.